Okay, so consider a pair of ellipses. Here's the outer one and an inner one. And they're going to be concentric, and the inner one is not necessarily axis aligned. Now the parameters, the semi-axis of the inner one, have been chosen so that this pair admits a one-dimensional family of Poncelet 3 periodics. What does that mean? It means that if I depart from a point P1 on the boundary of the outer one, and I find one of the tangents to the inner ellipse, and I follow along that chord, and I meet the outer ellipse over here, and I repeat this Poncelet iteration, I'm going to go back to P1. Okay. Of course, if I had not picked these parameters to be correct, for example, I made that inner ellipse be have its the minor semi-axis be smaller, you can see here that the Poncelet iteration is not going to take me back to P1. So if I continued this iteration, I'll probably fill space like so. But I want to consider now, or I want to assume now, that the parameters of the inner ellipse, tilted inner ellipse, concentric, have been chosen so that, so here's another example, I can close the trajectory. Okay, very well. Now let's draw the circumcircle of this triangle. Here's a circumcircle. It's this dashed magenta circle here. The center of the circumcircle is represented here by the symbol X3 after Kimberling's encyclopedia. Now the first thing you notice as you traverse the family is that the locus of the circumcenter is an ellipse. Now this one is actually a little unfortunate because it's touching, almost touching the cosec. So let's change the inner ellipse a little bit. Let's make this inner ellipse be perhaps fatter. I'm going to make it be a little fatter like that. And yeah, so maybe I want to do this. Okay, so let's consider this case here. Okay, now let's draw the circumcircle again. Okay, this is better. So I have the circumcircle of this 3 periodic. Of course, I can investigate or observe the circumcircle over the family. The center, denoted X3, is denoted X3. Now, the first phenomenon we notice here is the following. The locus of X3 over the family is itself a concentric ellipse, and its axes will be invariably aligned with those of the inner ellipse. So that's a pretty nice fact on its own. We also notice that the circumradius, reported up here as r, is variable. So as I traverse the family, you can see that that big R is varying. If you accept that the locus of X3 is an ellipse, of course, the distance between O and X3 is going to be variable. So I'm reporting that distance here. There it is. So now we have a situation, we have a family of circumcircles whose radius, circumradius, and distance to the common center are variable. Now let's recall a concept from basic geometry called the power of a point P with respect to a circle, centered on O and with radius big R. That power of point P with respect to a circle is simply defined as d squared minus big R squared. Okay, so it's the difference between this first distance squared, this distance d squared, minus the radius of the circle squared. So if my point P is inside the circle, my power of P with respect to the circle is negative. If I'm outside, the power is positive. And if I'm on the circle, of course, my power is going to be 0. So let's return to our experiment here. And I want to report now what's the power of O with respect to the circumradius of this family. Here it is. It's a negative number. What is surprising is that this power is invariant over the family. So that's the first phenomenon. Now let's draw a second circle. Let's draw the Euler circle. The Euler circle of a triangle, or also known as a 9-point circle, passes through the 3 midpoints of the sides of a triangle. So you can see here that this dashed green circle, you cannot really see it, but trust that we've done the right thing here, and the circle is indeed passing through the 3 midpoints of the sides, and it's passing through 6 other points. Okay, now the first thing you notice here, I want to choose another example. So I want to tweak my inner ellipse a little bit so that we get a more dramatic effect. So what am I going to do? I'm going to make the outer ellipse be wider, and I'm going to make my inner ellipse be perhaps skinnier, so I get more asymmetries here. Let's increase this guy so the system is more asymmetric. I still have a 3-periodic family. Okay, now let's just check the previous result. I'm going to draw the circumcircle. You can see here that the locus of the circumcenter is still an ellipse that is axis aligned with the inner ellipse. And I'm reporting big R, distance from x3 to O, and the power. Now notice that the power remains invariant. Now let's go back to the example with the Euler circle. So here's Euler's circle. Okay, this is better. So you can see here that this is clearly a circle passing through the 3 midpoints of the sides. Okay, so it cuts the sides. Here's one midpoint, here's another midpoint, and here's a third midpoint. Now here's Euler's circle. Its center is called by Kimberlin x5, x sub 5. Now it turns out that over this family, this center will also move along an ellipse. However, the axes of this ellipse are not aligned with either the axis of the outer or the inner one. They're sort of rotated to be in their own position. But the locus of x5 is an ellipse. Now, because this locus is an ellipse, the distance from x5 to O, reported up here, cannot be constant. And because the circumradius, as we saw before, was not constant, it is a well-known result that the radius of the 9-point circle is half the circumradius. Right, so here it is. The radius of a 9-point circle is half the circumradius. So this guy can also not be constant over the family. So if you just watch this number and that number, they're varying. However, the power of O with respect to Euler's circle is negative in this case, and also invariant. So we have these two interesting observations. Both the power of O with respect to the circle and the power of O with respect to Euler's circle are invariant over a 3-periodic family interscribed between a pair of concentric ellipses, not necessarily axis aligned. Is this going to work for the confocal pair? Here's the confocal pair. Let's turn these two guys off, and let's make the outer ellipse perhaps less concentric. Let's draw up the confocal pair. This is also known as the elliptic billiard pair. Let's draw its circumcircle, its Euler circle, and let's check if those powers are conserved. Because the system is more constrained, namely the inner ellipse is now also not only concentric but axis aligned with the outer one, you get extra symmetries here in that the elliptic locus of both the circumcenter and x3 and the center of Euler's circle x5 lie on ellipses which are themselves axis aligned with the outer one. You're going to get the same phenomenon if you go to the so-called homothetic pair. Let's make this guy be a bit more eccentric. Let's reduce this, and let's get the homothetic pair here. So you're going to get, again, you have a pair of ellipses, no longer confocal but homothetic and axis aligned and concentric. So you also get constant power of the center with respect to both the circumcircle and the 9-point circle. So what we notice here is this seems to be a deeper property of the generic case of two concentric ellipses that admit a 3-periodic family, where the inner ellipse is not necessarily axis aligned. So if you draw, so here's the case that I was just describing. Okay, this seems to be a phenomenon that can be generalized to this situation. And that x3 is always going to be riding on an ellipse, as will x5. However, the ellipse that x3 rides on is axis aligned with that of the inner ellipse in the concentric pair. Now what happens if I translate the center of this ellipse a little bit to the right and a little bit to the top? So let's do that. I'm going to translate this ellipse a little bit. I'm going to perhaps make it be something like that. I'm going to translate it up a little bit. So now I have a totally general position, right? So yeah, so let's do this. I'm going to make this ellipse be a bit wider like that. Okay, I'm hoping that I can find the configuration. Here's a configuration which admits a 3-periodic family. Okay, now I can draw again the circumcircle and the locus of the circumcenter. The locus of the circumcenter is also an ellipse. However, the axes of this ellipse will not be axis aligned with either the outer or inner ellipse in the pair. You cannot perfectly see it here. I'm going to try to tweak this a little bit so this difference becomes more apparent. But these axes here are no longer axis aligned with those of the constant. Okay, and neither is the power of O with respect to the circumcircle constant anymore. Same thing is going to happen to the Euler circle. It's still going to be riding on an ellipse, so we retain that. We retain the fact that the locus of x5 and x3 are ellipses even in this general situation, this general configuration between two ellipses that admit three periodics. However, those ellipses are no longer axis aligned with either one of the ellipses, the original ellipses, and nor are the powers of the center with respect to either the circumcircle or the Euler circle constant anymore. You can see that these two numbers here are going to be varying. Okay, so for those powers to be constant, you have to go back to the situation where the ellipse pair is concentric. Hope you've enjoyed this. See you in the next video.